Is light really made of photons? What was the evidence for these particles in the first place? In this episode, Chantal Roth will present us with a provocative alternative viewpoint. That what we've long assumed to be proof of photons, phenomena like the photoelectric effect, Compton scattering, and the blackbody spectrum, might instead reflect how matter interacts with continuous waves of an underlying medium. In this video, we will revisit foundational experiments and ask ourselves questions such as, are discrete detection events evidence of discrete particles? Or can they arise naturally from resonance and wave phenomena? All of that is coming up here on Inductica.
Ready?
I'm ready.
Okay, well, so if the universe were some kind of elastic continuum, some kind of medium, we have already talked about what it means for special relativity and general relativity, but it actually implies that everything has to be composed of waves or rulers and clocks. So how can we justify this hypothesis that our matter and light is composed of waves? So this is what we're going to talk about today. And so far, we have mainly focused on two hypotheses. So the first one is that the whole universe is essentially filled with some kind of continuum. And I've tried not to be more specific on purpose because, also I saw in the comments, some people were asking, well, could it be this kind of structure? Someone wrote to me, well, could it be some kind of both Einstein condensate? Well, maybe, right? We can, but it's really easy to get down into the weeds, and then we just speculate. And so I wanted to keep it really simple and just have the fewest assumption necessary. So let's just say it's some kind of elastic right now. And so the second hypothesis, which we'll focus today, is that in this model, everything has to be some kind of excitation of this medium. So fields, light, matter, charge, everything has to be either some kind of wave or defect or standing wave or soliton wave in this continuum. So now, of course, people were like, oh my God, how could you say that? It's funny because just yesterday, actually, I saw this discussion between Tim Walden and Sabine Hossefelder. They were arguing about, are there particles? And Tim was going on about, oh, it's all abstract. And no, the fields are abstract. There's nothing real. I'm like, wow. So,
Tim
and to
Maudlin said that?
well, yeah, he was arguing that there's nothing connected to 3D space or anything like, because Sabine was kind of seemed a bit more reasonable. She was saying something about, like the vacuum excitation, which kind of sounds like a little bit what we were talking about, right? And so anyway, so the point here is, because some people might say, well, is what we are saying just quantum field theory? And it's kind of related, but here what we're doing, we want to have an ontology, right? We want to have a mechanical basis for all of this. It's not just a mathematical abstraction in this weird configuration space. We are saying there's something real. So that's the main difference between quantum field theory and what we are saying. But of course, there are reasons that, people would object, because they would say, well, there's the photoelectric effect and there's the blackbody spectrum. These are all proofs that there are particles. So this is what we'll talk about today. Try to address these questions. So let's start with something that's maybe not as controversial, phonons. So phonons is something that we see in real materials, okay? It's not in the ether, but in real materials. It could be metals, it could be in crystals. People study these things to see how heat moves, maybe in a computer, right? You might need the heat sources. It's important that you know how the heat moves around. These are sometimes called particles of heat or quasi-particles, quantized sound waves. And here I have a demo that kind of illustrates this. So this is just a normal crystal or elastic solid, nothing to do with ether so far. And these are well studied. These are just oscillations. There could be circular oscillations, transverse. There could be linear oscillations, right? All very easy to understand. And the interesting thing is, nobody in their right mind here would say, oh my God, this requires parallel universes, right? Because the wave function collapse. Nobody would even think of that here, right? This is obviously, you can build this in your living room, okay? You can have springs and spheres, and you create these waves. There's nothing strange about it, right? Literally nothing. um, so the interesting thing is that how are they actually described? They are described very similar to photons. They are also quasi-particles. They have the same kind of energy momentum description. Now, the difference is that these waves are real. And also, this is from Wikipedia. Here it says it's a collective excitation in a periodic elastic arrangement of atoms and molecules in condensed matter, specifically in solids. So a phonon is the quantum mechanical description of an elementary vibrational motion in which a lattice of atoms or molecules uniformly oscillate at a single frequency. So when I saw this like years ago, I read this, I'm like, well, if this is described like a photon, and it looks the same, it's a transverse wave. Well, not, of course, it cannot be so longitudinal, but here, if you look at transverse waves, why are we treating photons so differently? What's the thing that's quantized here, right? So, and when we have a real mechanical model, like the living room springs with the spheres attached, it's very easy to understand what is quantized. So
I have a
imagine,
question though,
yeah, sure,
when you're
go ahead.
ready. So, with a phonon, um, a phonon is not what mainstream physicists would call a classical wave. It's a quantum wave, right?
What depends what you mean with classical, because
Yeah, well, I mean, that's part of the problem. The classical quantum dichotomy is a
yeah,
false one,
yeah.
but here's the point I'm trying to make. Like, that's just a conceptualization that's wrong.
Mm,
But here's the point I'm trying to make
mhm,
because I wouldn't use that dichotomy myself. Photons obey the Schrodinger equation. So whatever's going on with photons, when they talk about quantum, they're talking about a certain kind of wave in the ether, a certain kind of wave in the ether that obeys certain principles. Um, Phonons appear to be the same thing, like they're describable with quantum effects, right? They're not.
yeah.
They're so that seems to indicate to me that um whatever's going on with photons that we don't understand, the quantum part,
Mhm.
is also going on with phonons.
Exactly.
It's not
Yes,
like
that.
phonons are a classical wave. And by this, once again, what I mean by this is like it follows a straightforward mechanics that we already understand where
Yeah.
each part is understood as acting on each other part.
Mhm.
Like phonons don't follow that. They follow like the rules of quantum waves, which we don't fully which is like a formalism that gives the right answers, but we don't fully understand it, right?
Well, there's two kind of quantizations that they're talking about. It's all often mixed up. So one of them is, of course, when you have a limited size of your
Hmm.
springs that are connected, right? Like even your violin or a guitar, right? You have two ends that are attached. Well, you can't have any kind of wave in between, right? You can have the lowest mode is both ends are attached, so you have this thing that goes up and down. Right, that's one energy level, I guess you could say, one vibrational mode, n equals one. Then you can have n equals two, right? The thing is, it's bounded because you have this, both ends are fixed. So you can't have 1.5 waves in here. That wouldn't work. It wouldn't be
Hmm.
stable,
Hmm.
right? It might vibrate a little bit, then dissipate, whatever. So you can only have configurations where the wavelengths they end up here the nodes end up here at the ends. So then you have the mode equals n equals 2, n equals 3, right? And that's what's quantized because you can only have certain vibrational modes. You can't have all continuous wavelength here because you have these boundaries, right? That's the
Yeah.
main thing that's quantized here. And that, of course, is trivial. I mean, in a way, right? Yeah, that's what quantization means. It doesn't mean that the amplitude is quantized. It just means the wavelengths are quantized. So you have these
Yeah.
vibrational modes, right? So that's important to understand. Now, the interesting thing is also that people have used these phonons with an N to do all kinds of interesting experiments. So they have been doing, um, double slit experiments with phonons, which I think is pretty cool. Now there are all other kinds of similar quasi-particles. There's polaritons and surface plasmons and all kinds of qubit type things. And you can do double slit experiments with this, right? Now, no, again, nobody would think, oh, this is magical. How, you need the parallel universe to split because one phonon goes left and the other one goes right. No, it's a wave, right? I think nobody would question that for phonons, where you have elastic movements going on, nobody's gonna wonder. There's nothing weird about it. It's just, but the fact that they're described just like photons, like why would there be such a difference for photons? Why are we making such a mystery about photons and conjuring up all these different mystical ideas about split universes and all that? When for phonons, it's not. We can literally see that, right? We can literally observe those waves because it's macroscopic, right? There are actually movies also on YouTube that you can see. Um, yeah, and there's even this is a paper here. I can put the link in the description then where they did this double slit experiment, also even a quantum erasure experiment. And again, the quantum erasure is something where people say, oh my God, this proves that there's like retrocausality and all that stuff. It doesn't, if you work in the wave model, there's nothing mysterious about it other than that it's a wave. The only mystery happens if you say, oh, it's a particle, like it's a localized little whatever particle, then you get into trouble because how do you explain these interference patterns? How do you explain all that? So, but with phonons, there's no mystery. And I think I assume the reason why they're doing these experiments is show, there's really nothing that mysterious about it, which is pretty cool. This is just a recent experiment.
So
So,
so it's understood that phonons um are mechanical waves. They're not quantum. They don't they don't obey the Schrodinger equation.
well, I mean, in the microscope, of course, if you zoom into the atoms, right? But I mean, this is, of course, you could argue deep down, right? Your spring in the living room is composed of atoms and electrons. Well, yeah, I mean,
Hmm.
if you want to go to the limit, of course, yeah, you will, but then you will see quantum effects from electrons and all that. And so but the wave itself, the macroscopic wave, the vibration, has quantizations because of it's limited, and these waves, these big waves. So I'm talking, these big mechanical waves. They can do they can interfere with each other. You can do quantum erasure experiments and all that. So that part is quantum only in the sense it's just on the macroscopic level, right? You have the waves are quantized in the sense that they have, you need the wavelengths need to add up, need to basically you need to have full wavelengths, right?
Yeah, see, I think the objection we might get legitimately from
Mhm.
mainstream physicists, this is a legitimate objection they'd have. They'd say, well, phonons are already quantum phenomena. So explaining a quantum phenomena in terms of phonons, well, it doesn't you're ultimately trying to make the argument that these allegedly strange quantum effects really might just boil down to a completely understandable motion of some medium.
Well, yeah,
Um,
phonons are
and you're
macroscopic,
using
right? You can actually film them. You can see the wave. You can see the interference. And again, I'm talking about the macroscopic wave, okay? I'm not talking about deep down
I
inside
see.
the atoms, the electrons that also vibrate. And of course, there you have the Schrodinger equation. This is a totally different level, right? We're looking at the
I
macroscopic
see.
wave. And these waves interfere and they create doubles. You can do a double slit experiment with them. You can do interference patterns. And these macroscopic waves are described like photons, but just on a much larger scale, right? And so
Okay.
obviously there's some parallelism there. You can do double slit also with photons. And you can do a quantum erasure experiment with photons. You can also do them with
Hmm.
phonons. But with phonons, nobody in the right mind would say this is about retrocausality. Because there, the wave is going through, you can see literally the wave, moving along. You can
It's
actually
clearly just a
film it.
wave in a medium.
That's my point. Yeah. So it's not
I
that
see.
there's no wave particle duality in that sense. So that's the point I'm trying to make here.
Hmm.
With photons, we say, oh, it's actually a particle, but also wave. And, all this mystery about, oh, is the particle going through the left slit or the right slit? Nobody in their right mind would ask that question for a phonon, right? Because it's literally, you can literally see the wave. You can literally see,
Because we know it's a wave. We
yeah,
don't we're not tempted to think of a phonon as a particle. There's no Yeah, we're not tempted to think of it as a particle. We know it's just a wave and that's it.
yeah, it's, you can see,
I
well,
see.
yeah, exactly. Nobody's asking, oh, did the phonon go through this slit or did it go through that slit? That's kind of weird question to ask, right?
Yeah.
It's like doing it in the bathtub. You're not going to say, did the water wave particle go through this slit or that one? No, that doesn't make any sense. It's a wave.
Yeah,
And
right. If it's all waves, it resolves a lot of these questions. Like, oh, it seems to be acting like a particle and a wave at the same time. Maybe it's both. Maybe there's but it's like, well, and you can ask like, oh, well, which way did it go through the slit? If we observe it, then one thing happens. If we don't observe it, all this strange stuff you're saying is just maybe the result of thinking of it as being a particle when really it's nothing more than a wave. And
yeah,
if we
that's
can
the point.
understand
Yeah.
it as being just a wave phenomena purely, all these strange things go away, including the apparent retrocausality of the quantum eraser, which
Yeah.
are we
And
going to explain that the details of that later?
I
By the
do
way,
have a demo on that, but this the one thing I might move to another episode because it could take a while to
yeah,
explain. So,
right,
but I
yeah,
do have the simulation ready. So definitely about yeah,
okay,
yeah, yeah. So yeah, the point is here, nobody in the right mind would say there's universes have to split in one universe it goes left and the other one it goes right. That would be ridiculous, right? I think everybody would agree this is ridiculous. But why is it ridiculous here, but not for photons, right? Why should it be, oh no, for photons, it's totally different. It looks the same. It's the same formula even. But no. Hey, there suddenly we need this, universe split and Copenhagen and all that stuff, right? You know what I mean?
yeah.
If you think about this, like, it's kind of duh, it seemed to me when I saw it like years ago, it seemed why would they think that? So of course we have to ask the question, well, obviously there must be some reason that people think it's a particle, right? Because if you just look at that so far, it's like, why, right? Because there's a lot of examples where we see light as waves, like refraction we talked about, interference patterns, right? We know all that from light as well. Polarization clearly means there's a wave character. We have coherence, Maxwell equations, right? The electromagnetic wave. So why do people think that photons are particles? Well, there are these three main, I think, experiments or results or observations. One of them is the photoelectric effect, where Einstein got the Nobel Prize. So this is a pretty strong argument, right? If we are saying no, it's not a photon, well, we gotta better be able to explain that, right? So that's a very big objection. The other one is Compton scattering, where literally, if you explain it with like billiard ball types photons, it makes sense. Yeah, you have the scattering, you can easily explain it, and the blackbody spectrum. So these are the three areas. I will focus
And
mainly on
let's
this
go
one.
into a bit of detail here. For Compton scattering, that constitutes an argument for the particle nature
Yeah,
because the way that a photon bounces off an electron, to put it crudely,
yeah,
is the same. It can be modeled entirely in terms of the collision of bodies.
yeah. You have
And
this
they're,
momentum, and you can draw the vectors and the
yeah.
angles and all that. It looks, yeah, it's like a very easy explanation, right? So, but that, of course, it doesn't prove it. It's just it kind of makes sense to look at this in terms of particles because we know this from playing pool, for instance, right? Or bowling or something. You can see how they bounce off, and people understand this kind of concept, right? It's a little harder to explain with waves. The thing is, we can explain it with waves, and I'll show that I have a demo later on that too.
Mm,
Um, but so these are the three areas we'll need to explain. At least one of them, I
yeah.
want to focus on one of them because the concepts are kind of the same for all of them.
Mm,
So we need to understand maybe one, this one I thought, and then once we do that, hopefully it will be easier to understand the other ones as well in
yeah.
terms of
And then with the black body spectrum, again, it's this curve for the spectral emissions of objects. Like this curve was found using the assumption that energy is quantized. And so one way to explain the quantization of energy is if, energy takes the form of individual particles, and that would
Yeah,
account
exactly.
for
Right. That's the easy way
quantization.
out. Like, oh yeah,
But
sure, let's just keep
yeah,
it up and that's it. Then we're good. So, but then,
something worth noting here is we're witnessing the failure of the or the possible failure of the hypothetico-deductive method here. Just because you
Mhm.
come up with an explanation that's consistent with the observations. Oh, when we model it as particles bouncing off of each other, we get the right results. When we make energy
Mhm.
quantized, we get the right results. And energy must be quantized because everything's made out of particles. That kind of reasoning doesn't prove anything.
Yeah.
And so we're in this situation where we accept a bunch of things that really haven't been proven. This is
Oh
why we got
yeah,
to go
and then
back
it's
to
written in books and people learn it in school and that's it.
yeah.
You have a whole
Yeah.
generation that yeah, that's it
Yeah, and
basically.
it makes it very hard to back our way out of these mistakes. And it's mistakes we never would have made if we used the method of inference instead of the guess and check method.
Yeah, I think so. I think you're right. Yeah. So let's talk about the photoelectric effect a little bit then. So that's where actually he got the Nobel Prize for showing that light is a particle. Now the thing is, the classical view was that the more light you shine, so the higher the intensity, then the faster the electrons should be emitted. So basically, you shine light onto like a metal surface, and then electrons get emitted right at some point. And they also thought that any light frequency should work. They didn't see a reason why it should matter, like what kind of frequency you use. And they also thought that, if you have low intensity, it would take more time than when you have high intensity. And the thing is, what they found is when they use higher intensity, they found more electrons, but they weren't faster. And the other thing, they also noticed that the frequency mattered. So it needed a minimum frequency. And they also couldn't see delay. Now the thing is, there is actually delay, but they just couldn't see it, right? I mean,
Mm.
this is actually I have a demo on this. This is like attoseconds. So, well, of course, you're gonna have, they couldn't see the delay because they didn't have the ability to measure, assume those time scales. Um,
Mm.
so now let's look at this a bit in a historical context, okay? So this was in 1921 when he got the Nobel Prize. The thing is, quantum mechanics didn't exist yet at that time. So there was no theory at all yet about how light could possibly interact with quantized matter. I mean, Schrödinger wrote his wave equation in 1926, and then in 1930, okay, this is when Fermi's golden rule was identified, which explains how a wave perturbation theory, how a wave can interact with an electron, for instance, with the electron energy levels. So at that time, when Einstein did this, that he didn't know about this yet, right? That wasn't common
Mm.
knowledge. Like this wasn't part of the theory yet. So I think he basically had no choice, right, to draw these conclusions. I think if he did that 10 years later, I think he would have come to a different conclusion, which is interesting too. So I think we should revisit. I mean, that's basically what you're also doing, right? Revisit some of these experiments and see what assumptions went into these experiments. What did they know at that time? Because now we know a lot more. If we look at these experiments again with our current knowledge, maybe we can come to different conclusions because we know a lot more, right? Do you know what I mean?
Yeah.
So let's talk briefly about Schrödinger, what he was actually thinking. There's a few quotes I like. So in 1926, he wrote that material points consist of or are nothing but wave systems. So he was convinced that everything is literally composed of waves. He also didn't like the quantum physical, the probability interpretation. So he said, let me say at the outset, I'm opposing the basic views from when Max Born put forward his probability interpretation. He was not happy about this at all. And also, he didn't like quantum jumps at all. He said, if we have to go on with these, I can't say that we're probably on YouTube, quantum jumps, then I'm sorry that I ever got involved. So he also didn't believe in anything instantaneous jumps, right? Um,
Hmm.
and this is not a quote I like, and I couldn't find the source of that, but I think it captures the essence of what he believed is What we observe as material bodies and forces are nothing but shapes and variations in the structure of space. I think that's just beautiful, no?
Mm.
I mean, that's really exactly what we're actually talking about, right? If there's some kind of elastic
Yeah.
continuum, he says structure of space, but you know what I mean. The word sometimes, but I think it totally captures what we're talking about, this elastic continuum, which is interesting. So,
I should note really quickly that I don't think, at least with what we know now, I don't think there's anything wrong with the dang quantum jumps because they're jumps between different we're trying to understand them as jumps between different resonance states. And there's no literal jump, but it's just that there's only certain kinds of absorptions and emissions that are required, and that's what leads to the jump from one state to the next. So,
yes.
but
Mhm.
it's no true jump. There's no actual discontinuity that we're arguing for. Maybe back then they were, and that's why he,
Oh, but people
referred to
still
them as the
say, like,
dang
in
quantum jumps.
discussions you hear, they're saying it's instantaneous, right? That's what they're
Yeah,
still,
right,
that's like
right.
what they're actually saying. So then,
I see.
before we can actually understand the photoelectric effect, we have to understand why matter could be quantized. What does that mean, right? And what's even the evidence that matter itself could be a wave? Because that's what he's saying. He's essentially saying matter is wave. So is that crazy, or what's the evidence there? And the interesting thing is there are quite a few experiments these days that show that matter has wave-like properties. So people have done double slit experiments, literally, okay, with electrons, with neutrons, with atoms. And I don't know if you've seen this, but they even with complex molecules like a C60 molecule. Yeah,
Yeah,
yeah. This is like a soccer ball shaped carbon
with
cage.
fullerenes. Yeah.
Of course, they what they did, they have like they do one at a time. They send one at a time, and so the molecule interacts with itself. So the which is really weird, right? So this whole soccer ball shaped thing has to go through, in a way, two slits, which of course really really narrow, which is pretty crazy to imagine, right? You imagine this rigid soccer ball. How can it go through two slits? So very interesting. And this is the image. This
It
is from the
makes you
paper.
wonder something. It makes you wonder about something. Our whole model of how molecules work.
Mhm.
I'll tell you something. Our whole model of how molecules work, about how they're a particular, they're particular bodies that have certain attachment points, their valence, and they attach to one another through that valence, and they have a certain geometric structure.
Mhm.
What I found is that this picture was proven entirely through an argument from coherence. I might be wrong, but from my study of the history so far, I found it devil like a little maddening. Oh, there was never an inference that proved this. It's all based on this self-coherent picture of a particular geometry. Now, what's interesting is that picture has been remarkably consistent, so there is a very high probability it's right. But it makes you wonder, well, if that geometric picture of the molecules, a bunch of parts, a bunch of bodies attached to one another is right, then how is it possible that they also interfere with themselves when they go through a double slit? Now, my first thought, for what it's worth, is that Bohm is right. That these particles have a wave pushing them around, and that the particle and the wave are separate.
Well, what I do, I mean, have a
That
single particle though going through two slits. How do you explain that?
Because the particle doesn't actually go through. The way Bohm would say it is that the
Oh,
particle
I see.
doesn't
Yeah,
really
yeah.
go through both slits. The particle goes through one, but the wave that guides it goes through both.
Oh,
And
I
that's
see. Okay. Yeah, yeah.
that's another hypothesis that's, worth entertaining. Of course, we're entertaining an entirely separate one, that it's all waves, and that the particle-like behavior is caused by particular aspects of the wave. So we're
Yes,
following
and
up here
I need to
on,
show you the
yeah.
next slide then, because
Yeah.
you should look at what his talk. He got I think he even got the Nobel Prize. Wolfgang Ketterle. This is from his
Mm,
work here. They created these Bose-Einstein condensates, right? Where this is one gigantic matter wave. So
mm.
a coherent matter wave, and this is we're talking about. This is a millimeter here, a whole millimeter, okay? And they can take pictures of these waves, which is pretty amazing. I
That's
mean,
incredible.
if you're telling
Wow.
me this is all just how could that be? Does it just, oh, it's all probabilities? How does that work? I mean, it just kind of seems weird that,
Yeah,
you know.
there's clearly, well, the thing is even look, even if the wave is just a probability wave, it's just like a wave that represents the probability of a particle getting pushed around, of a particle being found, and there truly are particles. Well, then there's still a wave phenomenon. The fact that the particle arrives in a wave type distribution and that distribution evolves over time as a wave, that's not just a mathematical model.
Oh,
Like
there's
the
got to be
fact
this
that a
wave.
wave
Yeah, yeah.
model
There's got to be
applies
waves,
means
right?
there's some kind of wave there. It means in this case, according to this hypothesis, it would mean that the ether has a wave, and that wave, as it evolves, guides the particle in different ways over time because of its evolution. So there's a wave. There's a wave here. There's no argument, a physical wave. It's not just a probability distribution. The fact that the probability distribution works means there is a wave because the only way you get a wave type probability distribution is with a wave type phenomena causing it.
Yeah,
Because the
exactly. Yeah, yeah,
probability
yeah.
distribution needs to have a cause. It can't just, oh, it just happens for no reason. That makes no sense.
Right,
So, I
right.
mean, it's philosophically corrupt to say it that way. So yeah, there's
Yeah. So,
anyway.
so there's quite some evidence that, matter has wave-like properties. And so you all know about, the Broly wave, where, he started to think about that, the quantization, using the N, where you have one, two, three, or four wavelengths. And I think I do have a demo on that also. Yeah, I do have a small demo on that also. It's basically just the same thing, like a circular version of the linear string. So if you imagine you have a circle and you want to have fold a wave around it, right? Well, you can just have one
Mhm.
circle, or you can have two, or you can have three. And now look, if we choose a value like 3.12, well, the wave ends, they don't add up, right? You get a mess. But of
Mhm.
course, you
Mhm.
can't. So you can't go from 2 to 3 to 4, but in between, it's not going to be stable because the wave is just going to decay, I guess, or fall into some other level. Um, so he figured that out, that somehow, matter has these quantizations. The electrons has these quantizations, and it has to do with waves. And when you do this super simple calculation, so you have like, you have a circle and you're trying to figure out how many wavelengths fit into it. That's basically all it is, right? The quantization of the waves. Um, it's really a very simple concept, and explaining this without the wave property would be really difficult, right? I mean, if how would you explain that? It makes perfect sense that you get those the levels automatically just by this very simple thought, basically. So basically, the idea is that there's a localized mechanical standing wave of some sort, um, and the levels, the quantum numbers we use describe the modes of this. And well, we have already seen it for 1D. Now we can also, of course, the electron is three-dimensional, right? And it's easy to see how it works for one dimension, but isn't the electron three-dimensional? So how do we get to 3 dimensions? So the next level would be, if you look at a drum head, a 2D drum head, when you have a drum and you hit it, there's different wave modes also. Let me just start that so we can see that interactively. So here we have, it's basically like quantum numbers, but just in 2 dimensions. So the lowest one is just the drum head, that membrane goes up and down. That would
Mhm.
be the quantum number one. And then we have quantum number two. It's still a spherical, well, not spherical, but it's a circular wave.
Circular. Mm.
But you have now additional, the wave is now, you have different wave, no,
We
the
have we
nodes here
have
are circle,
we
right?
have three nodes, it looks like, or
There's
one
two.
node, one,
Yeah. Well,
two,
here the blue line here is where it's zero. So where you have an actual node that, um,
A-
we
and
also
on the
have,
edge, right?
yeah,
The
now we
edge
can
counts as a
quantize that
node.
further. So we have additional modes, and the higher we go, the higher the energy level also is, the higher the frequency is. So
Now,
the,
I have a question. You're raising the azimuthal um quantization.
Mhm.
Um I tend to think of L, the azimuthal quantization that you're increasing, that you've now increased to three, and it produces this cool pattern. I think of that as angular momentum. But when I look at this picture before us, I don't see any angular momentum going on here. I don't see anything rotating. Am
The
I
aha. Well, we'll
Or
see.
am
We'll
I
see.
am I just missing the implicit rotation in this?
Well, right now, I think for 2D, it's a little bit different from 3D. So in 2D, um,
Hmm.
we'll see it in 3D when we do the 3D
I
wave.
see.
Yeah,
Okay,
yeah, yeah.
cool.
Of course, so
Cool.
we can go to higher and higher levels, right?
Yeah.
And it's yeah, and it's pretty clear. I mean, it's pretty clear how this quantization works, right? So there's no
Yeah.
mystery about that. Now, let's do that in 3D. So this, I think it just looks cool. I just love that. To look
Yeah.
at that stuff. So there's two, yeah. So these are the typical spherical harmonics from hydrogen. Now I
Hmm.
left out the N just because let's imagine this was actually acoustics, right? So we can get again the simple one is just like imagine you have like a metal sphere and you're hitting it,
Hmm.
right? You have this, it goes out and in. That's basically what it
Yep.
can do. And the
Yep.
next level, like you have the wave going up and down. Now we can actually I thought I did have, oh yeah, I do have this, well, it's kind of exaggerated, obviously, but how it would vibrate in a way, right? Like if it was purely acoustical, like what it would look like, just to visualize it better. And you get these interesting shapes, and this is just spherical harmonics, right? There's nothing, yeah, there's nothing weird about it. Like there's nothing magical, or it's just plain
It's just
old
a vibration
acoustics.
in
Okay, it's
something.
literally you can take a metal ball, you hit it, you will get these kind of shapes. Of course, in a metal ball, it might look more like this, right? So what I'm doing, I'm exaggerating the visuals, of course, a little bit.
So I have a question. Couldn't we, from my understanding, oh, that's cool. From my understanding, couldn't we indeed get vibrations like this and like the non-spherical ones? We could get these non-spherical vibrations inside of a metal ball, right? It would just
Yeah,
be that the vibration,
yeah, like this.
how
Like
would you put
so,
it? Like, I mean, it just doesn't vibrate throughout the entire ball. It's just like
yes.
it's I mean, we can think of, here's the way I'm thinking of it.
See, yeah,
The whole black background is a medium, and
yes.
we're
Mhm.
seeing a vibration in part of it. We're just highlighting part of the black thing
Yes, it's an
in white
isosurface.
in
Yeah,
order
it's
to,
yes, exactly. Mhm.
okay,
Yeah,
yeah,
it's like an
just to make
isosurface.
sure.
Like we're showing a particular amount of displacement. We color that in different colors or something like that. It's just,
I see.
but I
So
have
this
another
white
demo.
surface represents
Yeah,
the
yeah.
set of locations at which a certain amount of deformation of the medium is
As an
found.
example, you can
And
color by
that,
energy or you can color, well, yeah,
okay,
yeah. So there's different ways to color this. And this is here, I was using actually the sphere, right? So you can imagine here, this one, this is actually a sphere, right? If I just exaggerate the movement a little bit, you can still see how it looks like. It's pretty cool,
hmm,
right? I mean,
yeah,
it
yeah,
looks
very
pretty
cool.
cool. Yeah. So this way you get all the different orbitals, and these are exactly what the hydrogen orbitals look like. I mean, that can't be, imagine why would this be a coincidence? What kind of coincidence would that be, right? Thinking about this, that, oh, yeah, it's all spherical harmonics, but no, 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 there's no wave. It's just mathematical. And by the way, the electrons, the orbitals, in chemistry, you use these lobes, right? You use these lobes to calculate how reactive a molecule, an atom is, for instance, how much
Hmm.
charge there is distributed. So these orbitals have real physical meaning, like
Yeah.
because I also studied biochemistry, and there you learn all about these orbitals. You really imagine how this orbital docks. There's this atom, it doesn't have, there's slightly positive charge, and then you have this orbital that fits right in here. You use the angles too, right? You calculate the angles to see how what the molecule looks like H2O, for instance. Simply you can calculate the angles based on the orbitals, right? So when you study chemistry, it's obvious there's real physical meaning to these spherical harmonics. It's not just mathematics. They have real a 3D space analog. So it's not just
Yeah.
nice math.
And
So
and something else I'll say is like this isn't just an argument from common sense. Now, it of course comports with common sense, but in one of my videos, and well, in several of my videos, I give the argument that because if you look at what a wave means, if you accept that the mathematics of waves successfully predicts what happens, then it means that what's happening under there is the result of certain properties.
Yes.
And then further, what that shows is because of the mathematics of the wave, that shows that the property at each location is being altered in accordance with the property at neighboring locations.
Yes.
And that's what a real physical wave in real physical entities means. So I have to emphasize, like, once you gain the right philosophic
Yeah.
perspective on this, it isn't just common sense. There's a proof of it. And you can see that in some of my other videos. I'll
Oh
link that
yeah,
in the
this is
description.
a great proof, by the way. I really like that. It makes a lot of sense. Yeah. I mean, otherwise
Yeah,
it's
I
just
think
magic.
that's
I mean,
that's
if
the
you
philosophic backbone of all of these concrete leads you're giving us. It's not, and these leads you're giving us are not, again, they're not just common sense. It like there's a real ether behind this, and we know that with certainty.
I would think so. Yeah, of course, as we go along the series, there are certain things I'm less certain about, but this one, I have no doubt really because there's no reasonable doubt basically, because everything else makes no sense. It's saying there's no either, no real wave, then we have all this magic, right? We don't know anything basically. So yeah, so here you have the actual hydrogen wave functions. I don't know if it's from Wikipedia or something like that. It's exactly that. And here I have another demo, which is uses particles, particle physics, just to show more that the 3D nature. I was trying to kind of visualize the displacement. I don't know if displacement looks exactly like that. Okay, this is of course
Mm.
an illustration, but if you imagine if there's some kind of elastic medium, you could kind of see how this could possibly oscillate, right? And
Yeah, that's incredible.
we can also like what we saw before the isosurface, we can see that here because we can, so overall it does still look quite spherical, but we can look at the amplitude. So this noise floor here, it cuts off the low amplitude areas more and more, so you can see more inside. And depending, of course, how far you cut in, shape looks slightly different. But again, here we have the N, L, and M. So this is the principal number, the azimuthal, and then the magnetic one that you were talking about. So here is a simple one for n equals 2. And then we have, this is right, the famous one. And then, of course, we have the magnetic one. And the magnetic one would rotate. I didn't add the rotation here, but in reality, this would actually be rotating. I just didn't add that yet. So when M is not 0, when M is 0, it doesn't rotate. But when M is not 0, so this would rotate left, for instance. And when M is, say, +1 or +2, it would rotate on the other side,
I
basically.
see, but it's just that we don't see the rotation because
I didn't add it.
the
I just
oh, I
didn't.
see. Okay, you just didn't animate it in. Okay,
No,
I
no,
see.
no. Because I just wanted to
Now,
look at the shapes of this. Yeah.
right. Now, what do the dots represent exactly?
Well, points, if we can imagine this elastic continuum, we just represent as a bunch of points, like a bunch of
Mhm.
dots, and they're connected elastically. That's basically one way to visualize. Now, this is just using random dots. Like if this was a jello, right? Imagine you had this
Mhm.
invisible jello and you random and put Smarties in it everywhere randomly,
Mhm.
and you see
Mhm.
how they move, basically. Do you know what I mean?
Right. Okay, and the noise floor
It just shows what's
determines,
colored. Like we don't color, like here we color pretty much everything. Here we just hide the Smarties that don't move. We hide the ones that don't move in the jello, basically.
or we hide the ones that are not moving sufficiently.
Yeah,
So
exactly.
here, so if you crank it all the way up,
Mhm.
crank it like way high, so that we can understand what you're doing here. Crank up the noise floor a bunch.
Now it's just,
Here,
yeah.
you're excluding all Smarties except those that move quite a lot.
Yes. Mhm.
And then when you pull it all the way back, then you're including all of the Smarties.
Yes. I'm not going
You're
exactly to
including
0. It's just
everything, even
close
if
to
they don't
0.
move all that
Otherwise, it
much.
would just be all colored. Yeah, yeah. It's very
Right.
cool.
And yeah, the problem with this is yeah, you lose a lot of the structure when you do this, which is why the noise floor is a really nice feature.
Yeah.
Yeah, that's cool. And yeah,
And it's just so fun to play around with
that
this.
the character. Oh, whoa, look at that. What did you do? What did you do
Oh,
there?
I changed, the
The
different
mode.
quantum numbers.
I
Oh, these
see.
shapes are so cool. Yeah. I mean,
Yeah.
some of these are
Yeah,
just,
I mean it's the 3D waving that lies behind the nature of matter. That's what we're looking at here.
Yeah, and of course, this would only be one
visualization.
aspect of the electron. I'm not saying this is the electron. Electron also has charge and spin 1/2. So this is just like the one aspect of it. So the
Mm.
whole electron
Mhm.
wave function is much more complicated, but it's one aspect, right? It's just like one part of the wave, basically. And later on,
It's the
yeah.
transverse aspect. I'm sorry, the translational aspect, the aspect of the electron moving around the nucleus, so to speak.
Yeah, basically the spherical harmonics when the electron is bound to an atom. This is basically, yeah. So
That is in contrast with the way that you're going to explain spin 1/2 to us, which, based on what I understand, is it's caused by an inner waviness of the electron.
you can still explain it the same way. It's just these points also move in a circle in a double loop. But I'll do that. I think next
Oh,
episode I'll do
okay.
that one. But it's all it all fits together. You will hopefully you will see that at the end because yeah, and I think at the end you will see it fits together because speed 1/2 is the origin of magnetism, right? So you
Hmm.
have that circular movement, and then we have the Compton frequency and radius. So the electron wave itself, there's some movement, there's some Titelbewegung, right? Anyway, I think it all fits together. This is just a spherical harmonics aspect to it. So we have totally. I didn't include charge or spin 1/2 here.
Okay.
That's normally what we see also. Like people don't. It also gets a little hard to see if you combine everything.
Right.
Now, there's an interesting paper I saw recently about acoustics. Okay, this is nothing to do with quantum physics, and really it was about acoustics, where they were saying there's like a way the transition between these acoustic states between the spherical harmonics. And I'm like, when I saw this, I'm like, oh my God, this is just exactly like we were talking about before. These quantum jumps, right? Maybe they're not instantaneous either because the formulas are known for acoustics. And I have a simulation on that too. So here, what we can do, I have, let's just use the same, or it doesn't really matter. So here I have two different states. I have, say, N, 3L1, M0, and then I have a different state, N3, L2, and M1. Now, what I can do, we can get from one state to another continuously. We don't have to jump at least based on that paper, right? We can get from one state to another one. I can just morph it continuously. It might
Hmm.
be fast, it might be fast, but there's the point here is there's a continuous function. It doesn't have to be instant, at least in acoustics, there's no, it doesn't even make sense to say that it's instant, right? Sure, you will have a messy vibration in between, but you can get from this state, for instance, to that state um,
That's so cool.
continuously, right? So
So
yeah, you can play endlessly.
let's get clear on what exactly we're talking about. So in these acoustic systems, we have some kind of medium, and there's an acoustical vibration,
Yeah.
rumbling around in every direction in 3 dimensions, and it settles on particular harmonics
Yes.
because of what, like the shape of the object? Is that why, or why are there particular harmonics in
Well,
this
just think
case?
about, a metal sphere as a music instrument. You hit,
Okay.
how does it sound? They're different. If you observe the vibrations on the surface of that sphere, how can it vibrate, right? These are just different, just like we saw before. But
Hmm.
let's say you have a certain sound, maybe just see, maybe you're in this state, this sound configuration, and then we can also show
Hmm.
it as right. This is a different representation here. Now, let's say you hit it differently, or you keep adding energy to it, right? You keep adding additional energy, and then at the end, it's going to be in this harmonic state. Well,
Mm.
it's going to transition from this to that, right? And there's
Right.
a transition. It's not like boom, it's there. So it's
Hmm.
not instant. The point here
Yeah.
is, even though this was a music, this is a paper about acoustics. I think, and of course this is speculation, but I would think that this would also apply to quantum physics. That it's not instant. We haven't maybe observed it, But if we could, resolve or observe this somehow, I'm convinced that maybe it's not the same path, but it's definitely, I'm convinced it's not instant either. So it's some process that takes time. This
I
is
see.
great because there's, evidence from acoustics. I think it makes sense to me rather than saying it's instant. I mean, how would that work, right? So,
Yeah, I mean, it would have to be a fundamentally, the only way that that could work is if it was some kind of unprecedented phenomena. Like it's just some kind of way of being that's completely different from everything else we've seen. But we're seeing evidence that it really isn't. It's a wave in a new medium, the ether, but
yeah,
it's still just a wave in a medium.
yeah,
And we can see evidence for that by thinking about waves in a sound waves in a solid and seeing how, for example, yeah, like if you have I'm imagining when I'm looking at this, here's what I'm imagining to make sense of it. I'm imagining a metal sphere hanging from my ceiling
mhm,
and I'm hitting it with like a rod, and when it does, it's going to create vibrations. I think they're going to be actually very high pitched vibrations.
mhm,
um and so, I want to say, because if you think about, if you were to actually hit that, it wouldn't make that much of a sound, and I think the vibrations would dissipate very quickly, I think. But it would make a sound, and what I'm imagining is that these surfaces we're looking at, these colorful surfaces, they constitute um, a surface of equal deformation. So, like
yeah,
at every location along this surface, that represents a set of locations that have a certain amount of deformation. And it changes over time.
yeah,
Why? Because the sound wave is reverberating throughout the sphere. And why does it look like this? It looks like this because of the way the sound wave reverberates back and forth off of the edges of that sphere and back. And so it generates these patterns, and there's only particular manners of waviness that will fit in the sphere,
yeah,
that will resonate in the sphere, and others will not. And that's why there's a
yeah,
pattern to it. That's why
yeah,
it isn't random.
yeah,
And if
exactly.
you add energy, you'll transition from one harmonic to the other, but it won't be instant. It will, like there'll be a chaotic canceling of all of these different modes until it settles on some new harmonic or combination thereof.
Yeah, exactly.
Yeah.
Yeah,
Okay.
so I think that was cool to see that paper. And actually, there are other papers also now in quantum physics, which I thought was interesting. There is a paper that says to catch and reverse a quantum jump mid-flight.
Whoa.
Yeah, yeah. I can send you the link also. So they were monitoring basically an electron in some particular state. They were able to kind of watch it, and then they were able to see when it was about to go to another state, and they could reverse it on purpose. So they could reverse that jump was already starting to happen, um, and they could reverse it. They said they could control it if they could allow the electron to go ahead and jump, or the energy level, whatever, or if it should be reversed. And this also says, right, the experiment, the results demonstrate that the jump evolution, when completed, is continuous, coherent, and deterministic.
Mm-hmm.
So I think that's a really important paper. And I think it totally gels with the other one, right? With the acoustic one that also says, well, it makes sense, right? To say that these jumps are not instant.
Yeah.
Um, so so I hope by now we can see the reasons why, say, electrons will be quantized, right? That the energy levels are quantized because of the spherical harmonics. That makes sense because you can't have half a wave or a third of a wave. So whatever states the electron levels that we have, they are quantized. So hopefully that is explained now. So now I think we understand that why matter itself is quantized. It's very natural because electrons are three-dimensional, and the spherical harmonics, it's obvious how this causes quantization of the energy levels because you can't have 1.5 waves. It has to, add up, right? So the second part of the mystery is, well, how can light then change these energy levels of the electrons, right? Because ultimately that's what we do in the photoelectric effect. There, light comes in, a photon comes in, and changes the energy of the electron all the way so it will actually even get emitted from the metal surface. So how can light change the energy level of the electron? And to do that, we need to know about Fermi's golden rule a little bit. Now, to get some intuition, very basic intuition about how waves could act like particles, just in principle, I have two very simple examples. Imagine, for instance, there's a storm over a forest, and a storm is like it's like a wave, right? And imagine there's no storm particle, right? It's not like big ball of, it's clearly a wind is like you can describe it like a wave. And once in a while, a tree will fall, and that's basically our detection event. So we see the trees falling, and if imagine there were beings that didn't know about wind, they couldn't see, and they would just see trees falling, they might say, oh, they're storm particles, right, hitting the trees. Similarly, earthquakes, we understand really well they're waves. They're actually they're both longitudinal and transverse waves in earthquakes. And also, once in a while, a building will fall, and nobody in their right mind would say, oh, these were earthquake particles, right? It's clear there's some resonance going on. The earthquake will start to shake a building more and more. If it hits the right frequency, the building will fall. And this is how a wave can create some event, basically, like a detection event. So there are other examples of resonance that are really well known. There's the Tacoma Bridge, where the wind created a harmonic resonance with the bridge. And after some time, it actually broke, which is pretty amazing, right? That a simple wind, and it wasn't even a storm, I think, could break a whole bridge. And also what's really well known is that you can sing a tone. If you manage to hit the right frequency for a glass, you can actually break it. And I think the trick is that you have to, with your finger, right, you try to create the tone. You can hear what the resonant sound is from the glass, and then you try to sing that same note. I haven't tried it, but that would be maybe worthwhile an experiment. And then if you hit the right frequency after some time, it won't happen right away. That's also important, right? That's an important concept here. This is not something the wind starts, boom, bridge is broken. No, this takes a while. It has to, it starts swinging more and more and more. Same with the glass, right? When you hit the tone, it's not going to break right away. You're going to have to sustain that note for a while until it vibrates more. It will accumulate that energy until it breaks. So I have this, and this is actually what happens in Fermi's golden rule. What it says that you need to have the correct frequency in order to be able to lift the electron from one energy level to another energy level. So here is the swing example, right? So yeah, it's kind of cute, right? So you have, I need to probably make it smaller because you can't really see everything. So here we have a kid on a swing, and the perfect frequency would be here. And if we are a little bit off the frequency, imagine you're pushing the kid, right? You're trying to hit the correct frequency, because then each time your kid goes to the left, you give it a little tiny push. And if you do that with the correct frequency, the kid will go higher and higher and higher.
Right. As opposed to like if you push him as he's coming to meet you, you're going to reduce his motion rather than add to it.
Like here, my off resonance. So you can see here, this would be the perfect frequency. This is totally off. Like I'm totally off right now, and I'm pushing kind of randomly left, right. Nothing's going to happen. You can do this forever, right? Nothing's going to happen. And we can also change the length of the swing. Of course, this will also, here we are near the resonance again, right? But if you change, anyway, so, and the thing is, it doesn't have to be perfect. So if the closer you are, the more likely it is, that you're gonna actually it's gonna actually increase the swing height. Of course, when it's way off, it won't work. But this is just resonance, and you don't need to be strong to do that, right? Of course, if you're strong, like if you give it a really strong push, it won't take as long, right? Let's say your kid wants to jump off the swing, right? So if you if you push really strongly, it won't, maybe 2 or 3 times, and then that's it, right? But if you're really weak, you push with one finger a little bit, it could take 5 minutes, who knows? But you can still do it if you get over the damping aspect of this. It's all about resonance, right? Getting the right frequency. So this is what basically Fermi's golden rule says, is that, so here we have a representation of different energy levels of the electrons. And the golden rule says that, there is a transition probability from one energy state to the next one. And it depends on the resonant frequency. So this is the typical, what you see in just normal lectures, actually, in quantum physics. I do have a link somewhere that explains Fermi's golden rule. This is well known. This is nothing, weird or anything. It just, the closer you are to that ideal the energy difference, the faster it will happen. So the more likely it is that it will happen. The faster it will happen. And also you can understand that it requires a certain minimum frequency too. Like if you push really slowly, well, nothing's going to happen, right? Like if your kid's on a swing and you push really slowly, well, you do need some kind of minimum, right? Otherwise, nothing's going to happen at all. Of course, in the case of the electron, it's a little bit more complicated than the swing because imagine we have like a rope. And it's now in this mode here, but now we want to get it into n equals 3 mode. So it's n equals 2 initially because we had 2 lobes, right? And now we want to get it to n equals 3. So as you can see, as we are injecting energy at the right frequency, the right difference of the frequency, over time, we will get it to n equals 3. So you could, in principle, do this with a rope also. Right. And again, this shows that this is a continuous thing. It's not instant, right? Now we are not n equals 3. And you can, in this demo, you can pick any level that you like, n equals 4. We can go from n equals 1 to n equals 4. It just might take a little longer, depending on also, as you can see how it starts to wobble kind of randomly. But over time, it will, when you get the right frequency and check the correct frequency, over time, it will reach that new energy level and then it will be stable again. This is essentially Fermi's golden rule. And, again, the closer you are to the correct frequency, the faster it will be. There's actually a nice YouTube video somewhere, I should find it, where they used real ropes. This one guy, he had a real rope in like a clear tube, and he added vibrations to it, and you can see the same thing. It's pretty cool. Oh, yeah, by the way, this is a paper by Sergei Rashkovsky. So he has several papers on all this. He has papers on the blackbody spectrum and Compton scattering and all these things. I think he explained, they're not all perfect, but it explains it really well, how you can explain all these things with a semi-classical model. That means semi-classical means the electromagnetic wave is not quantized, but the atom or the electron is quantized, the energy levels of the atom, and how you can get, an event like this, like a detection event, using a continuous electromagnetic wave, but a quantized electron. It's really all about, resonance, the energy levels, and Fermi's golden rule. There's also, I will add this link maybe to the description. There's a nice teacher here that explains Fermi's golden rule, the paper, and so on. And also, there's some more details to this. When you look closely into the formula, and I'm not going to go into the details, but basically what you can see is, I think, let me just go there. What you can do now, based on this formula, right, we can calculate, well, if we change the intensity, what happens when we change the intensity? And what we can see then is that as we increase the intensity, the faster it will happen, right? So here, for instance, if we use this kind of intensity, the mean time is 9.5, I think, femtoseconds, right? Or something like that. And the rate. So based on this, right, we could, now this is pretty quick, but we should, try to do experiments where we do this, where we lower the intensity to see whether we do actually see that time difference, right? There should be, and I think there has been some experiments, right, where they saw attosecond time difference or something like that. So it's not instant as like in 1921, they thought, oh, it's instant, right? Of course, it's very fast, but I think nowadays we have the equipment to do these experiments to see, is it really instant, or is it actually, does it actually depend on in intensity? What we can also see is the frequency, and the minimum frequency required, and also that when you increase the frequency, you have more density of states. So you have more possibilities for the electron to go to. That makes it
Mm.
easier. That makes it easier than when you have increased frequency because the electron it doesn't have to go from state 2 to 3, right? It can go from state 2 to 27 or from 2 to 8 or from 2 to 29. And so there's many possibilities, right? At the lower end, though, there are not many possibilities. Like from 1 to 2, there's only, there's one basically. So this is here you can see that the higher the frequency is, the more possibilities the electron has to go to. And again, the paper is linked here. So this really explains the photoelectric effect because it explains that the detection depends, it's just a wave, an electromagnetic wave interacting with spherical harmonics, basically, with the electron energy levels. And there's nothing mysterious about it. So you don't actually need a particle for this, right? So far, we have not used any particle at all. The only particle in code we used is that the electron is some kind of localized in space, right? It has some 3D shape of some sort. And of course, we can call this a particle, but it's really we have only used the wave description for. We have not used anything that requires an actual particle. There's also a paper about the double slit experiment. It's really pretty clear, right? It's the same thing. So basically, in that semi-classical explanation, what we have double slit experiment. So we have the wave is actually a continuous electromagnetic wave. It's not quantized in any way. And the interference of course happens like as you would expect with a double slit. And the detection is just that where you have higher intensity, right? You have a higher probability of triggering this energy level difference, right? What we were just talking about before with Fermi's golden rule, the wave, as if it has the right frequency, it will interact with the electron, and the higher the intensities of that wave at that point, the more likely it is that one of the electrons is going to respond and react. Whereas when there's in these places where there is no amplitude at all, right, no intensity, then of course you're never going to trigger an event like that.
You're never going to knock a tree down.
Yeah. So this also means really we don't even need a particle riding the wave, right? It's not
Yeah.
necessary. I mean, of course, we can always speculate, but unless we have a reason to do that, like why would we add this
Yeah.
on top of that?
Yeah.
Like, it makes it more complicated. And how does the particle move? And what is that particle again? It's like kind of recursive. So
Yeah.
I
This is
think,
ultimately why I like your kind of hypothesis more than the de Broglie-Bohm. Well, it's not a matter of liking it. It's I epistemologically favor yours because it involves less assumptions about the entities involved.
yeah. And it's very risky. There's so many different ideas, but a lot of times people add all these additional things. And then
Yeah.
you need to justify that, right? Because once we start speculating, the chance that this is correct is getting lower and lower also, right? I mean,
Yes, every
so
every new assumption you introduce that doesn't have evidence that proves it, that independently proves it, every assumption you introduce, all other things being equal, makes it less likely that your hypothesis is true.
because also we are humans, we make a lot of mistakes. I mean, I make mistakes every day, many times. And when you have like 50 assumptions, some of them are just going to be wrong, right? I mean, right now we have two, so I'm still pretty okay. I'm comfortable with two. We are still okay.
Yeah,
Two
it's just
hypotheses.
yeah, it's
So,
now I have a question though. Isn't it seems to me that how do I say this? It seems like if we go down this path, we're gonna need a new wave mechanics
why new
because the
made mechanic?
current yeah, we're gonna need a new wave mechanics. It seems to me. Correct me if I'm wrong here, but it seems to me like we'll need a new wave mechanics because the current wave mechanics, as part of quantum mechanics, that is a wave mechanics meant to track the probability of a detection event. But but that is according to this hypothesis, that's an emergent phenomena.
Oh, here it is.
It's a
Yes. Yeah. But it's the same. Like,
yeah.
it's just basically it's just intensity. It's connected to intensity. What we call
That's the
probability.
way Reshkovsky did it,
Yeah.
but his is his. It seems to me like his framework, he calls it, it's called semi-classical because we have a
Mm,
classical photon and then a quantum electron, but he's presuming the quantum nature of the electron. But as we've said, the quantum nature of anything is just a result of this Schrodinger equation, which, like I
yeah.
said, it's
Mm-hmm.
just designed to find the probability of a detection event. And that detection
Oh,
events
I see
are
what you mean. Yeah, yeah.
emergent phenomena. So this is why it seems like we would need a whole different wave mechanics, which would explain the thing that's causing the detection event, which is primarily
Oh, I
these
see what
these
you mean. Yeah,
waves in
yeah.
the medium,
Mm,
but then also the way that the receiver conditions the nature of the detection event. That would need to be explained in terms of the wave mechanics also, because
mm,
what determines whether a detection event happens, it's not just the nature, it's the nature of the wave causing the detection event, but then the nature of the wave that's receiving that photon. Basically, the electron waves in matter are receiving those photons, and the photons either successfully make them
mm.
jump to another energy level,
Yeah.
or you could kind of say it analogously, it either breaks the glass or doesn't break the glass,
Mm,
right? It's kind
yeah.
of the same
Yeah,
thing. It
yeah. It's the
either
same thing. Yeah.
causes that jump or it doesn't cause the jump.
Mm,
It seems like the our ticket is to find a wave mechanics that describes all of these different phenomena in terms of one ether and shows how the Schrodinger equation is a result of all of that, which just tracks the probability of
yeah, yeah, yeah. I think quantum physics is
transitions or
fine in
detection
terms of the
events.
math. I think it's totally fine in terms of math. It just describes the surface of this all, and what's missing is the details. Like the inner workings are missing right now.
Yeah.
So quantum physics is perfect. Like just calculate probabilities.
Yes.
It works to great precision, right? So I'm not even questioning any of that at all, right? So I'm totally happy with the formulas. Oh, all good. It's just it's unfortunate though that they use this configuration space with all these dimensions, which makes it really complicated to map back to reality because that configuration space is not 3D, It's like when you have two
Yeah.
particles, you have 6 dimensions. So it makes it harder mentally to figure out, well, how do we get all this math mapped back to reality? So there's some work to be done there. So it's not a one-to-one mapping, right? It's just ultimately, as you were saying, yeah, Schrodinger equation describes the probabilities and the intensity, but there's more, we need to figure out in the inner workings, right? um because also like with glass, when you mentioned the example with glass, when you sing the note but it doesn't break, well, it started to vibrate and heat up a little, right? And maybe with the electron, it probably also started to vibrate a little, but it didn't make it. So is there some other, I don't know, is there any way we could
Is there
see
some
that?
other change that
Yeah, I don't
happened
know, right?
in it? Yeah.
Could be other things we haven't even thought of. So I think it's important to understand these processes, but I think it will take a long time to do that. I mean, it's also very difficult, right, to make these measurements and all that. So, but that quantum jump I mentioned, that the one in transition where they were reversing this jump, this is going in that direction, basically. Oh, by the way, yeah, he also has a paper on this Wiener experiment, which is, it's funny, I haven't really seen this before described anywhere, and it's really totally simple. It's really, really simple. That's why I want to explain it, because it makes it really hard to explain with particles. So it's totally simple. So we have just a light wave coming down here, okay? And down here, there's a mirror. This gray bar is a mirror. And now we have just a photofilm. That's all we have here, photofilm, right? And we can tilt that film in any way we like. Of course, the angle is really, really small in a real experiment. So we can tilt that angle, and that's what Wiener did. So when we do that, and of course, we make it so that the light is obviously in such a way that the mirror, when it reflects, it creates this interference pattern, right? So you can see there are places where there's high amplitude and places where there's zero amplitude. And this is actually from Rashkovsky's paper, also the code. So he wrote the simulation himself, and then I just kind of migrated it to JavaScript. It's a very simple one. So you can clearly see, understand how this works with a wave, right? It's trivial, right? Because here in these dark areas, you can see, right, there's a lot of there's blackening of the film, and in the places
Mhm.
where there's the note here. There's no blackening of the film, right?
Hmm.
Now, I haven't even tried this, but try to explain this to me. If there are particles, how would that work? So,
Hmm.
I mean, how would it even work with a particle? I don't even know how to explain this if I tried with a particle. With a wave, it's trivial, but how would that even work with a particle, right? Like, what would the particle be doing if there were particles? I mean, I don't know if you can imagine that. Maybe something to think about. What would the explanation be that, um, yeah, I mean, how this would work. Anyway, so this is a
Right.
very, very simple experiment that shows also the wave nature of light and explains it really easily, right? And again, this is all done with the same formula as I was showing before. There's nothing mysterious about it. It's just using continuous waves, and the only thing that's discrete or is the detection event itself. So what we call a photon is really the pixel on the screen. We see it. It's funny. Yesterday in that discussion they had with Tim Malden and Hossefelder, he was talking about, oh, we see the photon hitting a screen. We're like, wow, they really believe that, don't they? I was thinking that, sure,
Yeah.
if you're naive, it looks like something hits the screen, but it doesn't mean it is a particle, right? I mean, it's just because it looks that way.
Yeah. And again, this is what happens when you accept without evidence the the existing science. Like if you personally don't know the evidence that led to the proof of, say, the existence of the photon, you'll accept that existence and you won't question it.
Yeah,
You won't be in a position to question it. Now, uh, you know, we all came to question it for different reasons. For me, it was just because I personally wiped the slate clean and said, well, anything past a certain point, I haven't seen the evidence for, so I don't accept it yet. And I think
yeah, yeah.
this is utterly critical for backing us out of the mistakes that we've made in physics in the last 100+ years. Maybe it goes back even further. I personally have checked all of the physics going up until about Maxwell's
Oh,
equations.
cool. Okay. Mhm.
Yeah, so I'm confident in pretty much everything that came before that. But
Okay.
there's a lot of, but that's not much, right?
Mm,
Like everything
mm.
we're questioning today came way after that.
Yeah, yeah,
So,
yeah, yeah. That's pretty crazy. So yeah, so the other one is the black body spectrum. I won't go too much into detail because otherwise we'll spend another. I have like several more slides here. Um, so the main, I think the problem, if you can summarize the issue I see here, let me just show the Raleigh here. So basically, they had the idea that when a body radiates heat, basically what happens, right? You turn that body vibration, this heat, into photons, well, into light, right? So there's an emission happening from ultimately the electrons to turn like the energy is turned from electrons and so on into electromagnetic waves. And they were just assuming that, I think, kind of a naive assumption that basically each mode had equal energy. So you get this Rayleigh Jeans ultraviolet catastrophe because they thought this is continuous. They just assumed it's continuous. And of course, they didn't know, I assume, about the electrons at that time, the energy levels again. So similarly, when you think about this, how can an electron, emit something? It's the reverse process, right? The electron is losing energy. It makes sense to say that this is also quantized, right? So, and as soon as you do that, yeah, you don't get this ultraviolet catastrophe. Also, it's kind of weird that they actually thought this would literally be an ultraviolet catastrophe because, I mean, when you have a hot body, it doesn't have infinite amount of energy. How could it create this catastrophe? I mean, it kind of makes no sense to me. It seems kind of naive to assume that.
well, I think the catastrophe is that the existing theory clearly couldn't have been true.
Yeah, yeah,
That's the
yeah.
catastrophe.
Hmm.
Yeah.
Yeah, and Rashkovsky, he also has a paper on this, and he actually uses a slightly different model. He is saying that based on his model, he would assume the spectrum to be slightly different based on the atoms used, based on the energy, based on I think how many energy levels the atom or there are in the atom or something like that. I haven't looked into detail, but that would be interesting to see, if this could be detected. I'm sure this doesn't sound like it would be difficult to see if there was actually difference. But the main point is this can
Wow.
again be explained without particles. We don't need particles to explain that. It's kind of the same thing. So you have a continuous electromagnetic wave, and it's the atom, the walls, and the atoms and the electrons that are quantized. Um, Same with Compton's. Well, not the same, but the Compton scattering also can be explained with waves. And again, I won't go too much into detail. I have a demo here and a paper by, again, Roszkowski, but also Schrödinger, he wrote about this. He wrote über den Compton effect. Now, unfortunately, I couldn't actually, maybe if you have it, I would love to read it because it's probably in German and I don't even know if it's, where it can be downloaded or something. I couldn't find it right away. And he also considered light as being a classical wave. And there is a similar phenomenon using scattering of waves in an using ultrasound. So basically, you add ultrasound waves to some medium, and then light scatters on these based on these waves. It kind of causes like a refractive thing, like a refraction. So there are examples, real examples in laboratory we can observe where waves scatter based on other waves, and it doesn't require a particle explanation. And also in the demo, I'm not going to go into detail, but hopefully it should be self-explanatory. If not, we can also do another episode maybe on some of these things if someone really wants to know more details. The main idea here is that this is essentially if you have a wave coming in, interacting again with the electron wave, there's like a recoil effect because the wave does have momentum. And it's like a Doppler effect because the electron is recoiling a little bit. You get a Doppler shift, right? And the Doppler shift, that means the outgoing wave loses energy. And that's what we observe, right? So the incoming light and the outgoing light doesn't have the same energy anymore. So that matches. And this part is easily explained with a Doppler effect. And otherwise, I don't think there's anything really that strange about it or anything. It's just it can be explained with waves. And of course, it's, I can see the reason why people think, yeah, it's easier to explain with bowling balls, but it can be explained with waves, and we don't need particles for that. So this has an explanation as well, basically. So I guess one question often people ask, well, what does a single emission, light emission look like potentially? And I'm just kind of speculating here, but the way I imagine it, like if you have like an electron, say, and it emits a pulse, let's say a short pulse, unlike, if there's no object in the way or it's not absorbed in any way, I assume it's probably, in all directions, right? So I imagine that this pulse would go in all directions. And then when we have a probe here, so what we can see is this, it's not going to be just one wave, right? And then stop. It's probably going to go just like the reverse of the Fermi golden rule, where we have to keep increasing the wave energy. And I think when you reverse this process, you would get something like several undulations, right? Like here, you would get several undulations. This is how I imagine a pulse would look like a electron photon emission, as an example. Then the other thing, what I've been wondering, and many people wonder about,
here's something I'd be interested to know. Can one emission like this produce more than one detection event?
Oh, it should be. I should be, right? It's wavefront. There's no reason.
Yeah. So it
Yeah.
produces a certain probability of detection events
Oh, absolutely.
in
That's
every
important.
direction.
Yeah. Like it could
That would be
on the
really
left and on the
interesting to
right.
see. It produces a certain probability of a detection event in any given direction. Whereas the
Yes,
common
any
wisdom
direction.
is that a single photon is emitted and the photon is this wave going in every direction, and then the wave collapses, and once that collapse happens, the detection event happens in one spot, and that wave can no longer produce a detection event in other spots.
Very good comment. Very good comment. Yeah. So I
And
think
so
this
yeah,
is
this is a way to test. I think there's something there's some experiment we can figure out here. You, me, and Henry were talking about an
yeah.
experiment like this.
I had some discussion I forgot if it was a person or not, or it was AI. But when I did that, it basically the answer was, well, the definition of a photon is the detection event. So if there's two events, by definition, it's two photons.
I see. So
So how
I
would
I
we?
see. So the way these experiments have been done in the past
Hmm.
presumed the existence of photons, and further, if more than one detection event happened, then that's the way that they determined that two photons existed to
Yes.
begin
So
with.
how
Which,
could
yeah,
we?
which is
I
circular
mean,
reasoning.
could we do that? Like have a single electron and then have that one electron lose energy? Like we can even, I don't know if you can even watch it somehow. I don't know. And then we know,
It seems do I would be interested to know if we understand the conditions under which a single photon got created and see if those conditions can cause more than one detection event. That's a question that needs to be answered.
well, it'd just be low probability, right? It would be because it's basically, uh, yeah, if the chance, if you have a single one, like a single emission, it will be extremely low probability. And then you have to multiply it, square it, right? You have the second.
Right, but
In
if you
that
did
sense,
enough
yeah.
trials, you'd find one instance where quote unquote one photon produced more than one detection event.
I think we should do some exper. Yeah, it would be nice if you could do some experiments like that. Yeah,
It'd be
exactly.
interested. I mean, chances are the experiment's already been done implicitly. We just have to dig up the
Yeah, right?
data.
Exactly. Yeah, yeah,
So we probably don't
exactly.
have to actually put the money in to do this ourselves.
And so one question I've always had is what is H? I don't know, maybe you just intuitively, I always had a problem with that and finding like really understanding what that means, the Planck constant, right? And
Hmm.
oh, and by the way, Fractal Woman, yeah, I want to mention her. She has some really good videos also on this topic, and she has been insisting a while ago that there's something wrong with the way this is phrased because it should be not per second, but per cycle, right? It should be per cycle,
Mm.
and I think she's right on that. I think the per cycle was just dropped because people are sometimes lazy, and the cycle doesn't really mean much, in a formula. So so that the way I imagine it, imagine of course this was a wave, but imagine if this wooden crank, and it takes some work to crank it around once, right? Like I can feel it that's how much work I do every time I crank it, and it has this
Hmm.
resistance. So when I crank it twice, I have to do twice the work. If I crank it three times the work. And basically that one cycle, once going around, that's the amount of work it takes. This is one cycle of the wave, basically, right? One cycle of the wave. So that's basically the work needed. It's like a conversion factor that says how much energy is there in one wave cycle. And so it makes sense to say, well, if I do this once a second, right, I have 1 h per second. If I do this twice as fast, now I have to work twice as much. you know, if I do it 10 times as much, I'm getting really tired. So, and then that makes
I have
sense
to
that,
do, I have to do, so if I do 5 cycles per second, then I'm putting five. In this case, I can see you've set H equal to 50 joules per cycle. Then I'm
yeah, something
doing,
like that.
if I
Yeah.
do, that's what you happen to put right now in this
Yeah. Yeah. Yeah.
simulation. If I do 5 cycles per second, then I'm doing 250 joules per cycle. That's the idea.
Yeah. That's why we have to multiply,
Or
right?
I'm sorry, 250
Frequency.
joules per second. 250
Yeah,
joules
yeah,
per second.
right. And the frequency, determines how many times you do this per second. So that's why
So,
we have energy is equal h times the frequency because it makes sense because you have more cycles per second, right? You have if you have a wavelength of one one per second, I guess
uh-huh.
maybe some kind of radio wave or something. Then the energy is just h one time h, and then if you have two the way you have to you double the frequency, you get this undulation twice, basically. And so to me, that intuitively makes sense. It's like imagine you're standing at the beach and the wave is hitting you in the face. you know,
Hmm.
it's a certain amount of energy in that wave that's hitting you. And then imagine
Hmm.
now you have double the waves per second. Well, now you have a lot more energy hitting you, right? It kind of makes intuitive sense that amount of energy in that one cycle, that's what we call H.
So, okay, let me get clear on this. So you're proposing that H is a property of the ether? Is that what you're saying?
Yeah, I think it depends on things like
And
the stiffness, and we can calculate it, I
Right.
assume,
There's like
because yeah, right? Because it's the yeah, exactly.
and there's different systems. And so it's so but H is I'm a little confused here because you're saying H is defined as the energy per second, per cycle, but really it's energy times seconds. Oh, I
Yeah,
see. But like per
per cycle.
cycle is hertz. So you can think of it as
Yeah.
joules per hertz.
Yeah, but because the way we determine the frequency and everything, the second has to go in there. I forgot exactly why, but it adds up with the units and all that. It just the cycle is what's missing. There should be a per cycle, but it's not. Of course, it's not really helpful to have this per cycle in it because per cycle is not really unit like meters we use. You know what I mean? Um,
Yeah.
but if you consider
Well,
what's the frequency mean? What does the frequency mean? It is how many cycles you have in a
yeah,
second.
so I think of frequency. A lot of people think of frequency in hertz, which is 1/seconds. I prefer to think of frequency as cycles per second.
Yeah,
That's how I
exactly.
think of it. So
So when
hertz
you
is
do
cycle.
that,
So hertz is cycles per second. Okay, so really we can think of H as um energy per cycles per second. You'd get the same units if you thought of it
something
that
like
way.
that. Yeah,
Is
because
that
if you
what you're
have
saying?
higher
So
frequency, you have more cycles in that 1 second. So that's why you have more energy also.
so oscillators with higher frequencies
Mhm.
have higher energy
Yeah. Mhm.
in proportion with H because the
Yeah.
higher the frequency, the higher the energy you have to
Yeah.
have per cycle in order to maintain that same value of H, which is uniform throughout the whole ether, apparently. Is that what's going on?
Something like that. Yeah. I mean, I think it's much easier to understand it that way. Like that it's really the energy, the amount of work or whatever per cycle, like per, yeah. I
The
used to
amount of work per cycle
action
for a
per
given
cycle
frequency
or the action per cycle. I think that I don't know if I used the correct term here.
action. The amount of work. Okay, so it's the amount of work per cycle. So no matter what cycle you're talking about, there's only 6.62 times 10 to the 34 energy units per cycle. It's just that some like oscillators have more cycles per second than others.
Yeah. Mhm.
Is that what's going
Something
on
like that. Yeah.
according to this
And you
hypothesis?
should,
Okay. I
yeah,
think getting
I'll
clear on
put the
this
link
would be a
there also
key
because she
part.
has some presentation about this also in more detail where she explains that. And
Mhm.
I think she makes a great point there because otherwise I
I
think it's
wonder
kind
if
of hard
this
to understand.
basically it I wonder if so so what I'm taking away from this is that we we need to we might want to reformulate what H means. It's not energy times seconds, but rather it's energy per cycle per second. And I'm
Well,
yeah, energy per I mean it's really energy per frequency.
yeah, we can. So she has done all the work. Maybe I'll link it and there's more detail to it
Yeah.
because yeah, it will take some time to
More needs
explain
to
all
be
the
done to
details. Yeah.
understand this. And
But
I
this
think
is more
maybe what
intuition,
this amounts
how
to
you can
is like
imagine.
it's a property of the ether. It's telling you the relationship between the amount of energy you have and the frequency of any particular vibration in the ether carrying that energy.
Yeah, I think it would also help to explain a lot of things. It makes it more intuitive if you think of it that way. So that you need a full cycle, for instance, for things. That's also where the quantization comes about, right? You can't have half a cycle doesn't do anything. You need the full wavelength, basically. It kind of ties back to the other quantization we talked about, like spherical harmonics, because you need the whole wavelength, right? Otherwise, you can't work with half a wavelength. So it's like a conversion factor in a way.
Okay.
Yeah.
I'd have to play with this to understand it better
Yeah,
myself.
it's an interesting thought, I think. Um, so I think what time is it? So maybe I won't go through all of this, but basically, the
Well, again, Chantel, we don't want I want to get the full 100% quality from you. So,
We can
you know, we,
also
we
maybe let's jump to the end. We'll have because let's just we can then cut it out. Okay. I also have the quantum erasing, but that will take longer. So maybe we'll do this another
yeah.
time. I think it's okay if we just jump to this now.
Okay.
This slide, yeah. So basically, so far, what we've seen that we don't really need particles. There has not been a single experiment that can't be explained with waves. So that's why I think this hypothesis is reasonable. It's still a hypothesis, right? Basically, because so what we're saying is there is a universe is filled with this elastic continuum of some kind, and everything we know so far, I mean, there could be other things we don't know yet, but the things we know so far, like matter and light and charge, everything is some kind of excitation of this elastic solid, whether it's a standing wave or a traveling wave or some kind of defect. And so far, we have not seen anything that requires particles. And I think we can continue on with this whole, hypothesis.
Yeah, this is very interesting. And I think continuing with this hypothesis will constitute working out a full wave mechanics for each different kind of oscillation, whether it's photons,
Mhm.
um, matter bearing particles, gravitation, and understanding that as different kinds of oscillations of the same medium, and how things like the Schrodinger equation emerges from that as a
Yeah.
description of when detection events will happen. But for that, we need a fully worked out understanding of what constitutes a detection event.
Yeah. And so that's the end of the episode. And next time we'll take a look at what spin is.
Thank you very much, Chantal. And that will naturally follow from a lot of what you've set up here.
Yeah, definitely.
Excellent.